Ladies and gentlemen, good afternoon and welcome to our webinar. I'm really excited that we have had so much interest in today's event. We've had over 300 registrations, so that's really a great sign in terms of interest for Bayesian networks and BayesiaLab. Let me start off by introducing myself. My name is Stefan Conradi and I'm the managing partner of Bayesian USA. And with me on the line is my colleague Stacy Blodgett, whom some of you may already know from telephone conversations and web demos. So let me talk about what we're going to do today. This is today's agenda. We'll briefly talk about motivation and background for all this. And I really want to keep this very brief and simple so we have a maximum amount of time for our examples. So I expect about 10 minutes for the introduction and then 50 minutes for the actual examples to work through. The examples we're going to look at are two examples pretty much from daily life, but as we will see, they're fairly tricky to reason about, even though they may look trivial on the surface. We will see how Bayesian networks and BayesiaLab can help overcome some of the cognitive limitations that we have. Just real quick, all the slides you see plus a recording of this webinar will be available later this evening, so you can watch all this again and look at the slides in detail. Also, today's examples are very straightforward, so you can easily replicate them even with the simple trial version. As you may know, we have two different types of trial versions. One, a very simple demo, or somewhat not simple, restricted, I should say. And then you can also apply for an unrestricted trial. But for today's topics, the simple demo will do. As always in our webinars, please submit your questions via the question panel. Even though we won't have time to respond to them live, you can simply submit them and we will respond to you via email, and we will also post the answers onto our user forum. Or rather, we will post both questions and answers to the user forum. But don't worry, we will post those anonymously, so don't hesitate to ask questions that you may think are perhaps silly questions. Every question is a good question, and perhaps others will appreciate if you raise a point like that. All right, let's talk about our motivation today. And let me begin here. Really, for 2,000 years or so, logic and reasoning have been very closely associated. And you know, when you have a conversation with somebody and this person may appeal to your reason, they may often say, just think logically about this. And that is not necessarily wrong to request logic in reasoning, but it is not sufficient, because what we need to realize is that logic is not enough. Let me share with you a quote in this context, and that is, classical logic has no explicit mechanism for representing the degree of certainty of premises in an argument, nor the degree of certainty in a conclusion given those premises. So that's a very, very important point. So you may ask, well, what do we do? Well, first of all, we need to realize that actually a lot of the reasoning we need to do in real life and everyday life really stretches across a broad spectrum in terms of the strength of arguments. Actually, very few things are on the side of pure logic. That's when you have 100% certainty regarding the conclusions and the premises. But a lot of things that we reason about are somewhere in between. We use premises and arguments that may either be strong or weak. That puts us in the space of inductive logic, which is really the biggest part pure formal deductive logic is just this tiny, tiny little sliver at the right end of this spectrum. So how do we deal with this? How can we work in this space if formal logic doesn't work in the majority of the cases? Well, roughly 2,000 years after Aristotle, Reverend Thomas Bayes has come up, has discovered, has realized how we need to reason with probabilities. What is now known as Bayes' theorem or Bayes' rule allows us to compute our confidence in an assertion given supporting evidence. So Bayes told us how we need to compute with probabilities, how to reason with probabilities. And again, let me share another quote to emphasize that. Bayesian inference is important because it provides a normative and general purpose procedure for reasoning under uncertainty. Now, you may think this is some arcane mathematical formula that is only of theoretical interest, but let me let you in on a secret, and that is human reasoning is very, very flawed, or can be flawed, and therefore this formula, Bayes' rule, is hugely, hugely important. There's an interesting book by Kahneman and Tversky titled Judgment Under Uncertainty, Heuristics and Biases. And that book provides many examples of how reasoning can go wrong. And one of the examples that I will share with you later is adapted from that book. But here I need to be a little bit more explicit or precise, because human reasoning is not universally bad. As it turns out, human reasoning in the direction from cause to effect is actually pretty good. It's actually fairly consistent with normative reasoning. So what we intuitively come up with in our heads, our intuitive response to a situation, as long as we reason from cause to effect, such as from disease to symptom, is rather consistent with normative reasoning, meaning what would be the proper result had we computed the situation with Bayes' rule. However, where things fall apart is when we go the opposite direction, such as, again, returning to this relationship between a disease and a symptom, with the disease being the cause and the symptoms being an effect. If we have to reason against the direction of causality, that's when really things start to fall apart and our intuition is no longer right. That's where we get into fallacies. And there's some very famous fallacies in that context, such as the prosecutor's fallacy that you may have heard of. And that is of great consequence in many situations, and there are probably lots of people wrongfully convicted or wrongfully acquitted based on that fallacy occurring in courtrooms today. So, and this is an interesting statement. Again, my final quote for today, that says, despite the mathematization of probability in the Enlightenment, mathematical probability theory remains to this very day entirely unused in criminal courtrooms when evaluating the probability of the guilt of a suspected criminal. So, and you may perhaps find that surprising, given that all the sophisticated stuff that happens in forensic labs and DNA testing, and you may think, how can things go wrong in this very scientific environment? Well, for that purpose, I want to share with you our first example and start to reason and highlight how reasoning can be quite tricky. So I'm going to tell you a story, and this is all about establishing the color of a taxi. So here's the story. The situation is that we have a taxi that was involved in a hit and run accident at night. That's what we know. As it turns out, in the city where this happened, there are only two taxi companies, the yellow cab company and the white cab company. The yellow cab company is the market leader. They account for 85% of the taxis in this particular city. 15% of the taxis belong to the white cab company. So 85% taxis are yellow, 15% are white. Nothing else. So now we have a witness of the accident that says the taxi that caused the accident was white. So that's the information that we have, and with that information, we go to trial. Now, we start our trial in a fictional country named Logiland, where formal deductive logic rules. Yeah, that's why they have a black and white flag. It's either this or that. So let's just go through our premises. We know taxi caused accident. Premise 2, two taxi companies in town, yellow and white. Premise 3, accident witness says taxi was white. Conclusion, the only possible conclusion, the white taxi company is responsible for the accident. Yeah, done. However, we live in likely land where we work also with probabilities. So instead of black and white, we have shades of gray. So at the trial in likely land, we also involve an expert witness who tells us about the accuracy of human vision under specific lighting conditions. And after assessing the situation, he says, given the light conditions at the time of the accident, the human vision would have an 80% accuracy in terms of distinguishing between white and yellow. So that's his statement. We can formally encode this in the notation of probability. So this would mean, given that the color of the taxi is white, given that the color of the taxi is white, with an 80% probability, the witness would correctly detect it. Conversely, in 20% of the cases, the witness would incorrectly determine or incorrectly state that the taxi is yellow. So same applies to the other way around as well. So that's our accuracy that we have. All right, you are now the jury in likely land, and you have to determine whether indeed the white taxi cab company is responsible for the accident. Yeah, we've heard everything. We learned the mix between yellow and white taxis on the road is 85-15. We have a witness statement that says taxi is white, and we have the expert witness who says we have an 80% accuracy in terms of the reliability of eyewitnesses. With that, I will literally make you the jury and ask you what you think as to what the probability is of the taxi actually being white. So please take a moment and let me know your answers. We're now collecting the responses, and then we will see how that relates to what we calculate very formally using Bayes' rule. So I'll just give you a few more seconds. I see that the answers are still rolling in. Okay, I will close the survey now. I think we have enough responses. And I will share the response with you now, what we have collected so far. And this is really quite interesting because we have a kind of a bifurcated or a bimodal distribution where we have almost the same amount of people who think the probability is in the 51 to 75% range and the 25 to 49% range. So it seems to be quite interesting. So obviously we have lots of smart people who are attending this seminar. So how come we are not in easy intuitive agreement in this regard? All right, let's find out what the correct answer is. Well, we can use Bayes' rule to compute the correct answer. We simply have to plug in the values we know, the premises, the expert statement, and so on. And with that, we can compute the answer. I will not give you the numerical value yet. We will see this shortly. Now, while this is the technically correct approach, it's quite impractical. You couldn't just do this on the back of the envelope. So you certainly couldn't do this in your head, and I would argue you would probably even struggle if you had to do this with an Excel spreadsheet. It very quickly becomes quite cumbersome. And bear in mind, we only have really one witness statement here, but in most real cases, we would presumably have tons of witness statements and perhaps disagreements among them. So what are we going to do here? That's where Bayesian networks come to the rescue. We're going to use our domain knowledge, what we know, what we have heard so far about the problem domain. We will encode this in a Bayesian network. And the way we will encode this is in such a way that it is in sync with how we naturally think about problem domains. So we will encode our knowledge from cause to effect, what comes naturally to us, where we are intuitively right. And then we will leave the more tricky part, reasoning in the other direction, reasoning from effect to cause. We will leave that to computer-aided inference. I'm calling it that casually. That's where we use Bayesian networks in BayesiaLab. Now, in previous webinars and seminars, we have used machine learning to create Bayesian networks. We have had lots of data and we used learning algorithms and so on. We performed knowledge discovery. Today, however, we have no data. We just have some premises. We have a witness statement, and from that we need to use. So what we will do today is we will encode our knowledge. We will literally draw this network ourselves and then use that for diagnosis. In a way, the witness statement is like a symptom, and we're trying to reason back to the cause, to what happened and who is responsible for the accident. So we're going to use our BayesiaLab software, of course. That's the software platform we can use for encoding knowledge, for machine learning Bayesian networks, for editing, performing inference, analyzing, and so on. But today, we will exclusively focus on the manual encoding part and performing inference. So let me just give you a quick preview of what the graphical user interface looks like. Very straightforward. On the left side of the user interface, we have what we call the graph panel. That's where the Bayesian network graph is encoded. And then on the right-hand side, that's where we have the monitor panel. That's where the little monitors reside that allow us to see what's inside the nodes that each represent a variable from our problem domain. So those two parts we will see, and I will now try to pause. Where is my button here? I will try to pause PowerPoint and switch into BayesiaLab. Just bear with me as I make that transition. Okay, now you should be able to see BayesiaLab, our graphical user interface, and initially you just see a big blank blue screen. Now we will open up a new graph panel. This is the canvas onto which we will draw our network. So that's what we're going to do now. Now we need to encode our problem domain into a network. So the first variable that I want to encode represents the color of the taxi. That's the node we want to infer. So I'm going into modeling mode or node creation mode and place a node onto our screen here. Let me just make this quite a bit larger. We won't need a lot of space for many nodes today. So I've just created the first node and I will name it taxi color. All right. And I need to define the states of my nodes now. Not of my nodes, of the states of my newly created node. So I'm opening up this node and the BayesiaLab node editor comes up. By default, new nodes have the states true and false, which is not appropriate here. So I will replace these two states with the states yellow and white. Okay, and in addition to defining the states, we also can apply a probability, because we know the marginal probability of yellow and white taxis on the road. We know 85% of the taxis are yellow and 15% are white. So absent a witness statement, that would be our expectation for any taxi that's on the road. So, but now we have a witness statement. I'm creating a new node and call it witness. I call it witness color. That's the color that the witness claims. And I need to do the same thing here. I'll just rename the states, yellow and white. Whoops. Okay, but for that node, I cannot provide a marginal distribution because that doesn't exist. You know, a witness statement only exists in the context of some event. So we're now saying that the witness color depends on the taxi color. In a way, the taxi color causes the witness statement or the witness belief regarding the taxi color. So I'm drawing an arc, in this case a causal arc, saying the taxi color causes the witness color. However, now what we heard from the expert witness, the accident witness isn't perfectly reliable, or human vision is not entirely reliable. So I can now encode the accuracy or the lack thereof in a conditional probability table that tells us what the probability of the witness color is given the taxi color. And here this is very straightforward. We learned this from the expert witness. Given that the taxi is white, the witness would say it's white with 80% probability, in the same for yellow. Okay, now we have a fully specified Bayesian network and we can perform inference. I will now switch back and I need to move my panel here. I will now, I will switch into validation mode and bring up the monitors of our two nodes. So here is the first one. I will make this a lot larger so you can see that. This is the node that represents the taxi color, and here is the node that represents the witness color. And given the probabilities we've provided, BayesiaLab has automatically computed the marginal distribution for the witness color. So, but that's not of interest. What we now need to find out is what is the probability of the taxi, or what's the probability of the taxi color being white given that the witness says it is white? Such a trivial question, but as we saw earlier in the poll results, it was easy to get a consensus. It was difficult to get a consensus on that. Now that we have our knowledge encoded in a Bayesian network, now we can use BayesiaLab to perform inference, and we can perform that in either direction. The direction of interest now is, let's set an observation on witness color to see what the taxi color is. Here in BayesiaLab, that is quite simple. I simply click witness color is white, and given that observation, given that piece of evidence, I now get an updated distribution for taxi color. The result is now that given this observation, there's a 41% probability that the taxi is actually white. So it looks like it's still more probable that a yellow taxi would have caused this accident. Conversely, we can just try this out. If this witness had said the taxi color is yellow, then we would know with near certainty that it was indeed a yellow taxi. And I wanted to share with you this example because this is such a typical example, and court cases are really very practical to illustrate this, because here everything depends on the base rate. What's the marginal mix of the colors? And therefore, this is also often called the base rate fallacy. And intuitively, we just get that wrong very often. So I would like to conclude this example now that most of you would have, actually 70% of you have realized that you got the answer wrong. Let me move on to the next example, perhaps a little bit more complex example. Let me try to make the switch again from BayesiaLab and go back to PowerPoint. And everything that you've seen so far, you will have screenshots in your slide. So you will be able to follow all of this. Okay. Okay, let's go to example 2. Also a very straightforward example. In fact, we've written about this particular topic in chapter 4 of our book, so you can read up on this in detail. So this example is taken from my life. So it's really a very real-world example. And this relates to a trip I took a few years ago from Singapore back to the US. Perhaps you know we have a small office in Singapore. That's why I travel back and forth between the US and Singapore like once or twice a year. Now, at the time I took this trip, I think it was like 4 or 5 years ago, excuse me, there was no direct flight between Singapore and the US. Now there are direct flights again, but at the time there were not. So I had to fly from Singapore via Tokyo and Narita, change planes, and then continue on to Los Angeles. So let me take you through this entire process step by step. So I check in Singapore with one piece of luggage. However, once I've checked in, there was a thunderstorm, or actually a typhoon, which delayed the departure, as happens so often. So I finally depart from Singapore and arrive in Tokyo. Unfortunately, I arrive quite late, so I'm worried about catching my onwards flight from Tokyo to LAX. So I race across the terminal building. I have to go through security again, and it's very much anxiety inducing, but I make it in time to my departure gate. So out of breath, I arrive, I get my boarding pass, ready to step on the plane, but then the gate agent says, yeah, I'm not sure your luggage will make it. Now, because that may not be transferred quickly enough between the gates and the terminals. So she says, yeah, there's a 50-50 chance that my luggage will make it onto my onward flight to LAX. So I get on the plane not knowing whether my bag is on that flight. I land, then I go through immigrations, all that stuff, go to the baggage claim area, and now wonder whether or not my luggage will arrive. So let's now analyze the situation. So I'm now at the baggage claim area. Luggage starts being delivered. It's coming down the chute. And now after 5 minutes of waiting, I still do not see my bag. So the question now is, what is the probability that I will still get my bag? Now, interestingly, most people just say, there's really no way how we can know anything. There's so little we know about the domain. There's really no proper way of reasoning about it. But let's think about this. What we want to reason, or what we want to infer, is whether or not my bag made it onto this last flight from Narita to LAX. So I want to infer, is my bag in the cargo hold, or was it in the cargo hold? And of course, I can't directly see that. I can't look inside. I don't have a tracking device. So based on circumstantial evidence, I now need to update my belief whether or not my bag made it. Okay, so here's the proposed workflow. I will encode my available knowledge, and admittedly, that knowledge is very, very limited. I'll take that, encode that as a Bayesian network, and then perform probabilistic inference given our observations. And you will see that that is quite useful, even though we know so little about this problem domain. Okay, I will leave PowerPoint again and switch to BayesiaLab. Just bear with me as I'm making that transition. Okay. All right, now you should see the BayesiaLab screen again. And once again, I will start from scratch with a new graph panel. So let's think about what nodes we need to represent here. Now, I already mentioned we want to infer whether my bag was on that last flight. So I will create a new node and call that new node my bag on plane. That we want to get an update on based on our observations. Now we have some information about this particular node, and that is we learned from the gate agent that our expectation is 50-50. She said there's a 50-50 chance that the bag will make it. So I can enter that as my assumption, as my marginal distribution. And by default, the states true and false are perfectly appropriate here. Okay, I'll set that to OK. And now we need to think about what we can observe, because there's really not much that we can observe. Again, as I said earlier, we can't look inside the cargo hold of the plane. What we can see are two things. One is whether or not our bag is on the baggage carousel. So that is what we can see. And so I call this node my bag on carousel, the baggage carousel. And that too has just two states, true and false. There's one more thing we can observe, and that is the time that has elapsed since bag started coming down the chute. So for that, I create a node and call that time. Now, of course, time is not binary, rather time is continuous, but I will keep things quite simple here. I'll just say our time horizon is 10 minutes, meaning that I expect all luggage is typically unloaded within 10 minutes. And there are some places in the world where that is actually true, such as Singapore. They usually deliver all luggage within 5 minutes or so. I don't know how they do it, but it really works there. So let me now change the states, the true and false states, and change that into minute intervals. I will now create 11 states from minute 0 to minute 10. Well, oops, no, that would be from 0 to 100. Let me change that. Okay, so now I have created states from 0 to 10, and time has a very attractive property, and that is that it progresses evenly. Every time slice, each time slice is as probable as another. So I can simply apply a uniform distribution. I do that by simply clicking complete, and then I have uniform probabilities across all my time slices. Okay, so now that is defined. My bag on plane, that's fully defined. Time is fully defined. Now we need to think about how these variables relate to my bag on carousel. My bag on carousel really cannot be defined independently because, of course, that depends on the states of the other variables. How? Well, I would argue that my bag on plane is a cause of my bag on carousel. You know, if the bag is not on the plane, then it cannot be on the carousel. However, if the bag is on the plane, then that will cause my bag to appear on the carousel ultimately. In a similar way, we should think of time. Because intuitively, I would say the longer I wait, the more probable it should be that my bag appears. So let me first just qualitatively draw this arc. So, and this is quite important about Bayesian networks because we have these two aspects of Bayesian networks. We have the qualitative structure through the nodes and the arcs, and then the quantitative part through the tables and conditional probability tables. So for my bag on plane and time, I've already provided the quantitative part. For my bag on carousel, we now need to do it. So let's open up the node editor for my bag on carousel, and similarly to what we did earlier with the taxi colors, now we need to enter the conditional probabilities. Now here let's start here. So the true and false columns, they relate to my bag on carousel. And then here on the side, we have my bag on plane and time. Now I would say the top part of this table is quite easy to fill out, because if the bag is not on the plane, then I would say it can never appear on the carousel. So this is very easy. I'm simply entering 100% false all across, and then simply complete and add the 0 for the true column. So that was easy. But now we need to think about, excuse me, what does that table look like for the true part, for the bottom half. Now, let's perhaps start with the simplest cases. I would say in minute 0, just as the carousel starts turning, there's a 0% probability because no bags have been delivered yet. Now, in minute 10, assuming it can only take 10 minutes to deliver all bags, then we would have 100% of the bags. And now I make the highly simplistic assumption that the bags are unloaded in a linear fashion, so that the longer from 0 to 10, my probability of receiving the bag increases from 0 to 100%. Let me fill in the other part of the column. So for the false column, then obviously the progression of values is the other way around. Okay, so let's accept that. Now we have a fully specified Bayesian network, both the qualitative part and the quantitative part. Now the question was, we waited for 5 minutes. We've waited for 5 minutes. We have not seen our bag yet. What is the probability that we will still get our bag? That's what we have to infer now from what we've observed. So I will once again start a poll and ask you what you think what the probability is that we will get our bag. Remember, a priori belief, the gate agent said it's 50-50. So she said she doesn't know whether the bags come across. So that was our original assumption. Now we have waited for 5 minutes and want to figure out what is the probability now. I'll just leave the poll open for a few more seconds. The results are still rolling in. Okay, now we have a majority that has voted, so I will close the poll and share with you the results. So this is the result. Now this is a much clearer picture. We have 45% of the responses in the 25 to 49% range. Then 23% believe it's under 25% in terms of probability, and a good amount think nothing has changed. It's always interesting. I like this example when I do this in a real seminar, because sometimes you get some really, really heated debates about, well, how one should reason about this. Okay, but let's answer the question. We can now use our Bayesian network. It's very simple. I am bringing up the node for my bag on plane, which is here. Then I'm bringing up the node for time. You know, I need to rearrange this a little bit so we can fit everything onto the screen and keep it large enough that you can see it. So now we enter our observations. We say it is minute 5. And we have not yet seen our bag. So I set my bag on carousel to false. Okay, here we are. So the probability, oh, sorry, I forgot to, I'm glad my colleague Stacy alerted me. I didn't switch back to BayesiaLab. Sorry, let me repair that. Okay, here we are. Thanks, Stacy. So here's the result. I've set evidence on time, and I've set evidence on my bag on carousel to false. And so given this observation, now the probability for my bag on plane has gone down to 33%. Let me just repeat that since you didn't see the process. So I said it is minute 5 and my bag on carousel is false. Yeah? So now we could ask a question, well, what happens in minute 6? Let me update that. So now we have set time to minute 6, minute 7, minute 8, and we can see where this is going. The probability is declining. We can more formally analyze that. Let me just remove time here, make my bag on plane the target node, and we can get a nice visual analysis of how the probability progresses. So this is what we call target mean analysis in BayesiaLab. On the x-axis, you have the time on it, and on the y-axis, you have the probability of still getting the bag. All right, now what we've done is actually quite interesting. What we have done here is what we call intercausal reasoning, because we have reasoned from one cause, that is time, via the effect, my bag on carousel, back to the other cause. And this is now, if you think the taxi cab example would have been difficult enough to compute with Bayes' rule, just think about how tricky this would be. So again, this is an example of how we can easily encode our limited domain knowledge here and then let the computer, in this case the Bayesian network and BayesiaLab, do the heavy lifting. Okay, let's make this a little bit more realistic. And let's say, so we stand at the airport still. We still wait for our luggage. We're still in minute 5. We have not yet seen our bag, but now we see a colleague. Let's say I see Stacy at the carousel. And I didn't see Stacy earlier because Stacy traveled first class, whereas I was in coach. And so we meet at the luggage carousel and discuss our itinerary, and we realize we've had exactly the same itinerary and therefore had the same tight connection in Tokyo. So now I see Stacy's bag. Now that I see Stacy's bag on the carousel, so she gets her bag that went through the same tight transit, how should I update my belief in me getting my bag? Okay, let's do that. Let's encode that. For that, I'm just realigning the nodes here a little bit. So I will now, oops, where are we here? Rearrange my nodes. I just copied the nodes for my bag on plane and my bag on carousel, and I'll change that to Stacy's bag on plane and Stacy's bag on carousel. Okay, let me just position this a little bit more nicely. And now I would argue that Stacy's bag on plane and my bag on plane are exposed to the same process. And I would call that the force that kind of affects both of them, the transit time. So I create a new variable that reflects how much time the baggage handlers actually had to move the bags from one plane, sort them, and wherever they go through the airport, and then finally load them onto the other plane. So I call that transit time. And again, I'm making assumptions here, and they're highly simplistic, but as we expand the model to get closer to reality, we could get more and more information and perhaps ask somebody at the airport, read statistics, who knows what. We could perhaps make better informed assumptions about this problem domain. But for now, I'll just say, in an ideal world, we perhaps have 100 minutes of time to transit all the bags. I think that's what the airlines tell you. If you have to make a connection, please allow for at least, let's say 100 minutes. And once again, I would initially assume a uniform distribution. Again, that's simplistic, and we can later on update that to something more real. So transit time, that now affects Stacy's bag and my bag. And what I'm thinking, the longer the transit time, the more likely is it that my bag gets on the plane. So if there was indeed, if we had 100 minutes of transit time, then there would be 100% probability of getting the bag across. If we only had 0 minutes, then there would be 0 chance. And again, I'm just saying that the probability of transit success increases. And conversely, I complete this column for the false column. And now the same applies, or I'm assuming that the same applies to Stacy's bag. But perhaps for her bags, since she's traveling first class, she may have all kinds of premium class stickers on there. Perhaps she gets preferential treatment. If I'm making such an assumption, I could encode that in here as well. But for the time being, I'm saying Stacy's bag and my bag, they're all equal. Okay, once again, we have a fully specified Bayesian network, and we can perform inference. Let's start. I'll just rearrange this a little bit. So, oops. Okay, and bring up my nodes. The first node is the node of interest, my bag on plane. I can observe my bag on carousel. I can observe Stacy's bag on carousel, and I can observe time. So let's repeat again what we saw earlier. Let's say it is minute 5. I have not yet seen my bag, but so the probability of getting my bag decreases to 33%, as we saw before. And just to come back to the poll, most of you were actually right with your intuitive guess. So that's really good. So now I see Stacy's bag. I set that to true. So now my probability of still getting my bag increases by 20%. Now we're at roughly 54%. So that's the information that comes through from Stacy's bag and updates my belief in my bag. So you may wonder, well, how is this really possible? What we have, again, is we have the flow of information between causes. But in this case, we don't just have the information flow from time via my bag on carousel to my bag on plane, but we also have the information path the other way around. So let me just illustrate that. We can very nicely visualize this with BayesiaLab. We can look at the influence path, in this case to our target node, my bag on plane. So here is the influence path number 1 from time via my bag on carousel to my bag on plane. And here is Stacy's path. And we can see that there is information flow via Stacy's bag on plane, via a transit time, ultimately to my bag on plane. So there's more information coming this way, and therefore I'm updating my belief in the probability as to whether I'll get my bag or not. Now you can see how we can easily extend this further and add many, many more elements. And we're running out of time to go through further such examples. Let me just show you a slide in this regard. Hold on, let me switch back to PowerPoint. No, hold on. Okay, now you should see PowerPoint again. We could now extend that model and think about beyond just looking at whether I see my bag and Stacy's bag. I could start counting bags and see, well, how many bags have been delivered so far? I could speculate about, well, how many bags do fit into a plane overall? What is the speed of unloading? All these things I can take into consideration to update my belief and to come up with a better estimate. So what I think is so fascinating here, that even though we know so little about this problem domain, by putting together what we know, by putting together our assumptions, we actually can reason about this properly. Now, of course, whether or not you get your bag or not, I mean, it's not a trivial issue, but it's perhaps not a life and death situation. But there are probably much more important cases where this type of reasoning might be important. For instance, we might want to reason about whether or not a patient will ultimately respond to the current treatment, continue the antibiotics, or stop that and try something else. Or you might want to reason about a search and rescue effort. What is our belief that the person or the ship or the airplane to be rescued might still be out there? Or in a business context, we may want to reason about, is the original business strategy working or not? Should we hold the course? Is it about to happen? Will success kind of come down the chute? Yeah, we just don't see it yet. So those are examples, and obviously way more important examples. And I think this type of reasoning, this type of probabilistic reasoning, can tremendously help in such contexts. So let me conclude. I think we have quite a few questions that have come in through the last hour or so. As I said, we will post the answers on our user forum. Now, hopefully you find all of this interesting enough that you might want to look at how to use BayesiaLab in your research workflow, in your everyday work. Please take a look at our website, look at the licensing options, configurations. You may want to take a look at our Bayesian store, where you can see everything from academic editions to perpetual enterprise-wide licenses. And if you thought this seminar was interesting and attractive, perhaps you may want to think about joining us again next week. And 2 weeks from today, next week, we'll talk about risk management without data. So it will be a somewhat similar example, but this time we're reasoning about the value of having a radar detector. Is it, and the risks we're taking exceeding speed limits. Again, an everyday life example, but I think it is useful to illustrate the concept of reasoning without data. Then on March 16th, then we will switch gears again that's when we'll talk about health policies with Bayesian networks. Now, we also, beyond these short webinars, we also have extensive courses, 3-day courses. Actually, one is running right now in Dubai. The next one here in the US will be March 13th through 15th in San Francisco. We still have space in that course, so I'd very much like to encourage you to consider that. It's a fabulous venue that we have for that course. It's actually the old Federal Reserve building, and we have a very nice large room there, so it should be really cool to host an event there. Please consider joining us for that event. So with that, I would very much like to continue the conversation with you, the dialogue with you. Please do feel free to reach out with questions, connect with us on LinkedIn, Facebook, Twitter, etc. And please do send us questions. We'll be happy to answer them. And with that, thank you so much for your time and interest, and have a fantastic weekend. See you again next week.